AWHI Hydronic Heat Working Group. Thank you all for stopping by. I think this is going to be an interesting one. Have to start out with the antitrust statement. So AWHI is a member-supported collaborative of professionals from across the U.S. This diverse membership includes numerous competitors, and care must be taken to scrupulously abide by federal and state antitrust laws. Members should remember that antitrust compliance is important at all times. At this and other AWHI meetings, participants should not discuss competitive pricing, profitability, allocating markets or customers, or promotion of a particular product or accessory. All right, let's get off and running. So the agenda for today, Peter can't make this one because I think there is an overlapping AWHI connectivity working group that he is attending to speak on. But I am here, so welcome. We're going to move to kind of opening the floor for folks to introduce themselves and, mention anything that is going on in the air-to-water heat pump world. And I'm going to give just a quick shout out to the manufacturer Roundtable, which happened on June 25th. And then we'll move on to our presenter of the day, Jonathan Woolley, who's here, who is going to be talking to us about multifamily electrification using air-to-water heat pumps. Really excited to hear this one. And then finally, we'll close. So first off, anybody who's new here, you can either come off mute or drop in the chat your name and organization and title pronouns, and we'll all say welcome. And you can do that while I am kind of raise your hand. Oh, Steve?
Yeah, so my name is Stephen Rogers. I'm the president of the Energy Conservatory. We're mainly focused on, measurement of buildings, but we do get involved in, heat pump retrofits as, our air tightness measurements affect loads, and we have some fairly innovative products for measuring airflow through HVAC equipment. And so we're sort of adjacent to the heat pump market, but very interested in what you guys are doing. We're also right now in the process of building a training lab in which we're considering whether we want to put a hydronic heat pump in that lab to demonstrate that technology as well. So happy to be here.
Yeah, thank you. What's the name of the airflow measurement product?
The TrueFlow.
It's the TrueFlow. Okay.
Yeah.
Used that before.
Yeah.
Matt. Welcome, Steve.
Hey, good afternoon, good morning. Can you all hear me?
Yep.
Great. Matt Robinson. I work at the Electric Power Research Institute in Knoxville, Tennessee. Our customers primarily the electric utilities in the United States, but Canada, across the world, also very interested, and we work with them. The group I'm a part of mainly we mainly work in evaluation of new to market thermal technologies. So a lot of air-to-water, a lot of air-to-air heat pumps, and starting to really get interested in air-to-water heat pumps at really the residential scale, commercial scale. It seems like, maybe these were popular 30 years ago. Everything seems to go in cycles. Yeah, trying to see how it could be useful for our customers, which is the electric industry. So thank you for letting me be here. I'm excited for today's conversation.
Glad you can make it. Madison.
Hello, I am Madison. I am currently an intern at GTI Energy, and I've done some modeling on electric heat pumps, and I'm going to continue doing some modeling with heat pumps here. So yeah, that's about it.
All right, Sarath. Is it pronounced Sarath?
Yes,
Sarath?
Sharath, yes, that's correct. So hi everyone, my name is Sharath. I'm also working at GTI Energy, also currently working with Jonathan in one of our projects, integrating air-to-water heat pumps. So at GTI Energy, I mostly work on demonstrations for new CO2-based or gas absorption heat pumps at military facilities, largely, or residential units. And currently, I'm also working with Maddie on modeling this system, understanding how to best integrate these units into current buildings to get optimal performance and energy savings.
All right, thanks. Welcome. Two more. We've got it's Charlie, right? Charlie McCracken.
Yeah. Hi, I'm Charlie McCracken. I work for Clear Result. I'm an HVAC trainer and a former contractor. Got started in the Carter era, energy efficiency. We run a program for Rhode Island Energy. Wrote the integrated control specification for Mass Save, which means absolutely nothing, just to be clear. And we are modeling heat pumps this summer, looking at air-to-water heat pumps throughout the Massachusetts and Rhode Island base that we can go and visit job sites. So anything that ends up in that local area, we'd love to visit. We modeled standard heat pumps 3 years ago, and we have an extensive heat pump rebate program in Rhode Island Energy for energy savings. Always interested in what's new.
Great, thanks, Charlie. And our last intro, Michael Dion.
Hey, yeah, Michael Dion here with Stiebel Eltron. I'm here to mostly just stay up to date with the state of the hydronic industry and how it relates to air-to-water heat pumps, with a particular focus on navigating the tricky and confusing refrigerant landscape, and as it's changing in the past year and the upcoming years. So, yeah.
Thanks, welcome.
Thanks.
Okay. Most folks know the purpose of this group. We are the group nationally who talks about air-to-water heat pumps. As the market evolves and possible standards evolve and use cases evolve, it is good to convene this group. We'd like to, in the future, take on some tasks that we can potentially do together. Right now, we're kind of in a simmering mode until we secure funding or otherwise identify something we really want to tackle. But it's good to convene and have these presentations and all talk together. Anybody have any new links to reports or presentations, any updates since, in the last 6 weeks that you want to give on activities or any upcoming presentations? It's kind of the middle of the summer, might be a slow day. All right. I wanted to give an update. So on June 25th, AWHI had a hydronics manufacturer, air-to-water heat pump manufacturer roundtable. I was the moderator, and we had 4 panelists representing LG, Stiebel Eltron, Chiltrix, and Enertech. These are all air-to-water heat pump manufacturers. Each of them gave a presentation where they, went over the capabilities of their air-to-water heat pump or air-to-water heat pumps. They tackled various things: installation guidance, options, metrics, things that are exciting and new. Some of them talked about multi-head configurations or cascade configurations, different hydronic distribution products. And then there was, some mentioning of the various other products that these manufacturers have, like heat pump water heaters. So that is available online, and I think Vidisha is going to drop a link in the chat to that if folks want to check that out on their own time. I won't kind of rehash everything that was talked about. It's 90 minutes, but it's got a lot of good content in there. During that, I did talk about our field study a little bit, so I just wanted to throw up a slide here that this is what I'm currently working on. We've got 3 retrofits live with air-to-water heat pumps. One is an LG single-family site. One is an Enertech single-family site, and one is a multifamily site with 2 Enertech heat pumps. But it's small multifamily, just 4 units in the building. And then we've got a new construction site that we're going to be installing M&V on very shortly. I'm texting with the installer, and he's, giving me updates on the electrical connections and when everything's going to be set for us to go out there and get our M&V in. The plan with this study is to monitor for across this next winter. We, due to delays, we didn't quite get in before the 25 or the 24-25 winter. So we're going to be aiming for the 25-26 winter for our monitoring. And 2 of the sites, the single family new construction and the single family retrofit with LG, have cooling. So we're going to be monitoring the performance of those systems across the summer as well. All right, made it to the presentation in record time. So I am going to stop sharing and pass it over to Jonathan Woolley, who is going to be talking to us about, now I can't see the title anymore and it was long.
It's a mouthful.
Modular, multifunction, multiplex air-to-water heat pump systems to streamline multifamily electrification. All right, I'll kick it to you, Jonathan. Thank you for coming.
Oh, you're welcome. Thank you, John, for having me. I'm really excited to be here and share with everybody. I'm excited for all of your questions and critique and feedback. So thanks for having me. So the core topic in this project is about the research that we're doing to try to address and compress costs for electrification in multifamily, and the ways that we're advancing integrated air-to-water heat pump systems, as we believe will help address that problem. So my name is Jonathan Woolley. I'm a consultant with Emanant Systems. Emanant Systems is really just me, but in that position, I have the opportunity to work with a lot of really excellent folks in the space, and all the work that I'm talking about today definitely involves a lot of collaborators. Most of the work is through a project that is funded by the U.S. Department of Energy through Lawrence Berkeley National Labs. It includes Oak Ridge, GTI. A shout out there to Sharath, who's doing laboratory testing for this project. Harvey Mudd College, Aris Hydronics, TRC, Gridworks, and most recently VEIC and Efficiency Vermont, who are collaborating with us on field installation of a R290 air-to-water heat pump system for a multifamily building in Vermont. So today, I'll talk as briefly as I can about kind of the core hypothesis that we have and what our project objectives have been and what we've been working on in the past few years to get to where we are. I'm going to spend a little time reviewing the challenges with the current practice electrification strategies for multifamily buildings, and then we'll dive in as quickly as we can and spend as much time with this multifunction air-to-water heat pump system that we've been developing for multifamily buildings. I'll talk about some of its advantages compared to the current strategies. We'll review some of our building simulation results. I'll discuss a bit how we've been working with Aris Hydronics and the grand prize that they won in DOE's Easy Home Electrification Prize. We'll talk a little bit about cost savings estimates for the system that we're working with. And then we'll round it out to discuss our current plans for a field demonstration of an R290 multifunction air-to-water heat pump system multifamily building in Vermont. So our core hypothesis and kind of the objective that we've been working toward is that designed strategically, we think that multifunction air-to-water heat pump systems can really streamline the pathway to decarbonize multifamily buildings from many different angles. And I've just been really excited over the past few years to see so many different threads come together that seem to be creating an opportunity for air to water, particularly opportunities for refrigerant conscious design, the capability of these systems to provide heating, cooling, and hot water from one integrated system. Their versatility and flexibility, the ways that they can allow us to retrofit existing buildings where the current electrification strategies fall short. And also the opportunity that air-to-water offers in regard to integrating with thermal energy storage and opening up kind of the emerging opportunity for demand flexibility from heating and cooling systems in buildings. So as I noted, most of the work I'm talking about today emerges out of a project that's run through Lawrence Berkeley National Labs, focused on reducing the cost of heat pumps for heating and water heating in multifamily buildings. And it's really a multi-pronged research project that has been running now we're near the end of our third year and entering our fourth year, and just starting up to do the second field installation. But it's included a bunch of market research, a single family prototype field demonstration with an R32 air-to-water heat pump, a bunch of iterative design and prototyping related to whole system design and integration, focused especially on like air-to-water and hydronics, but also a lot of work focused on advancing the design of phase change material thermal energy storage. We've been doing a bunch of laboratory testing, particularly of the R290 air-to-water heat pumps that we're setting up to install in the field. Lots of cross-cutting modeling work, and LBNL and Harvey Mudd College have really been taking the lead on developing some open source modeling tools to get these technologies out there. And now our field experiment. These are the threads I'll really be highlighting today. Okay, so I'm sure a lot of you think about this all the time, but let's review some of the challenges with current practice electrification strategies for multifamily buildings. And what I'm focusing in on here, and kind of the multifamily archetype that we're holding in mind for this project, emerges out of a lot of market research that TRC has been leading as part of the project. They've spent a lot of time working with and interviewing building owners, manufacturers, contractors, installers, to understand among those multifamily buildings who are electrifying heating and domestic hot water, why are they doing it? How are they doing it? What does it cost? And where are the pinch points and challenges that they're encountering? They're, in areas that are advancing electrification, multifamily buildings are kind of falling behind the curve, and we want to help them to move forward. So we have found, largely that the most common strategy is to utilize these multi-split heat pump systems with multiple indoor units in each apartment, like one in each bedroom and one in the living room, and then to use unitary heat pump water heaters, which are largely appropriate for single family residential. But when you have multifamily building that already has unitary water heating in each apartment, and you want to do heat pumps, this is the strategy that's being adopted, even in cases where, say, there's central domestic hot water in the basement. A lot of folks are using these unitary heat pump water heaters all ganged together. And I'll note that I'll talk a little bit more about this in a little bit, but I think this is a bit different than kind of the common strategy for adopting heat pumps in small apartments several years ago, which I think would have advocated to do like one indoor unit sized for the load of the apartment and then hope that you achieve adequate thermal distribution. But we found through this market research that a lot of designers are really advocating that you use multiple indoor units in order to actually achieve good thermal distribution in the space. So here's a little, picture to plant in your mind about the basic archetype that we're talking about. When we're thinking about design for multifamily, right now, we're really thinking about low and mid-rise garden style, loaded corridor type buildings. We probably want to adapt some of our designs for high-rise buildings. But we've put together kind of this little schematic to show you what an overwhelming amount of infrastructure really has to come together in order to do the common this common practice electrification with multi-splits and unitary heat pump water heaters. 1 outdoor unit per apartment, 3 indoor units per apartment, 1 unitary heat pump water heater per apartment. And all of those need new electric circuits that most typically get tied back to the sub panel within each apartment. And they do that, of course, so that each apartment can be individually metered. But that objective really creates a big challenge. Not only do you have to pull new copper from each of the sub panels to outside or often up onto the rooftop, then we also have to pull new copper from that unit up on the rooftop down to each of the indoor units in the apartment. New circuits for the heat pump water heater, and in the coldest climates where where the most common, even cold climate heat pumps won't cut it all of the time. Designers are including kind of emergency electric resistance, and if you want that to be integrated into the control schema of the system in any sophisticated way, it becomes a rather complex set of and costly set of controls integrations. Not to mention all of the line sets and all of the refrigerant that you have to use to fill all of these home run piping distributions. One of the things that we've learned in talking with contractors that are executing these retrofits is that oftentimes it's not just the new copper and new circuits and the work that you have to do within each apartment to electrify all of these things, but as soon as you touch the electric circuits, you often trigger the need for an apartment panel upgrade. And if you're upgrading the apartment level panel, you also have to upgrade the service level entrance and the meter. Sometimes this might even trigger requirements for meter grouping. And so the price for a project like this can easily skyrocket because of all of the infrastructure requirements. Here's a little summary of a lot of the challenges that we see. A dismaying amount of infrastructure, challenges with accommodating unitary heat pump water heaters, such as accommodating sufficient airflow, causing local overcooling, the cost of ductwork. The need to well, this is an interesting one. We noticed that to a large extent, those multifamily buildings that are adopting electrification are doing so only as part of a deep energy retrofit. And the causality on this relationship is interesting. It's and uncertain. Like, is it only because doing a deep energy retrofit can reduce loads far enough to make electrification worthwhile, or is it, and I lean toward this direction, the case that it's only worthwhile to do this amount of infrastructure upgrade if you're already planning on tearing apart the building and doing a deep energy retrofit? And if that's the case, we're really limiting kind of the market for decarbonization by kind of requiring that we can only do it as part of a total building overhaul. And of course, that often results in long displacement periods. So now let's talk a little bit about our ideas with using modular multifunction air-to-water in these buildings. In general, as you're all familiar with, we're talking about using air-to-water heat pumps to provide heating, cooling, and domestic hot water through an integrated system. And doing that in a way where heat pumps can provide heating and cooling to like a buffer storage volume that then gets distributed out to different types of hydronic emitters, and then having a second and separate tank system to provide domestic hot water. And this is generally what the system can look like. I love to toggle back and forth between these images when I'm talking to people about the alternatives, just to highlight what a significant reduction in infrastructure can be gained through the type of system design we're talking about. And I'll show you in a minute some more detailed schematics, but really what we're talking about is a reduced number of heat pumps on a rooftop or site located elsewhere, tied into a central electric circuit that's powered off of a house meter and a house subpanel. And then in this building archetype with distributed unitary hot water, we have distributed thermal energy storage. We're using these dual volume type tanks that have an indirect style domestic water heating, plus a buffer tank within a single cylinder. We're designing to locate one in each apartment and then package that system together with all of the circulators that you need and electronics that you need to control distribution to local fan coil units and or baseboard convectors, radiators, radiant floors. But largely we're focused on fan coil units, especially we think that in this size of apartment, we can, and by doing kind of this micro zoning, we can, in almost every application, get away with using low voltage fan coil units, and thereby, with the system design, completely eliminate the need for in-apartment electric work while achieving full-on electrification of heating, cooling, and domestic hot water. Because the electronics associated with these local storage tanks are really only very low power and can be plugged into the wall with an existing 120 volt outlet. All right, so just to run through some of the advantages that we see: reduced piping and insulation, reduced electrical work, reduced construction complexity. We hope by doing these things, reducing the impact to residents in the way that they're displaced during such projects. Of course, we're focusing in on using low-cost polymer piping, so not only are we reducing the piping length, but ideally reducing also the kind of the life cycle costs of the physical materials. So reduced refrigerant use, of course, reduced risk of refrigerant leakage because we're consolidating all the refrigerant in the outdoor monoblock style systems, avoiding the need for apartment level subpanel upgrades, reducing electric circuits, reducing peak demand, reducing the number, capacity, and footprint of heat pumps, and a few others which I may have mentioned here. We can come back to if you like. I just saw, John, your question. Do you retain multiple residential sized heat pumps because of minimum turn down ratios or some other reason? Is it cheaper? Let's come back to that later. There might be some of the things I'm sharing in the slides that will answer that for you. And if I don't, why don't you ask it again? And Charles, I see you ask about 24 volt fan coil units. Yes. There are a few manufacturers out there that offer 24 volt DC fan coil units. They can be wall or ceiling mounted, and it allows us to do all of the indoor electrical as a class 2 circuit. Okay, so yeah, now let me dive into telling you about this mouthful of a phrase that we've adopted in talking about these systems as modular, multiplex, multifunction air-to-water heat pump systems. Multiplex being a concept that the modeling team at LBNL introduced in this project several months ago. So here's the, looking a little bit more detail, a schematic of the system design I was just talking about. We're talking about having multiple monoblock type systems modularized, so you can have as many as you need to satisfy the loads of the building, heating, cooling, and hot water. Working together in a coordinated fashion to distribute heating, cooling, and hot water through two separate primary distribution loops that serve the entire building, or at least kind of grouped sections of the building. One of the primary distribution loops serves heating and cooling to the buffer storage tanks, and the other primary distribution loop serves domestic hot water. So here's what it looks like. Say we have one tank that needs, say we have one buffer tank in one apartment that needs heating. Well, this one heat pump is going to turn on at a low and variable speed to satisfy that demand. And then as the load in the building increases, we've got now a couple apartments calling for heat. That single heat pump is going to ramp up in speed. And then as the building load continues to increase, we'll invoke operation of more and more of the heat pumps in that array. And then as some of the apartments call for domestic hot water, we can begin to initiate from the other end of the array, domestic hot water operation for those heat pumps, distributing now through that second primary distribution loop and into the indirect water heater in each heat pump. That heat pump can increase in speed as the domestic hot water load increases, and the load between heating and domestic hot water can be shared across this array. So to be clear, all of the heat pumps in this array are set up in a way that they can provide heating, cooling, and hot water, and we can have any number of them operating in either space heating and cooling or domestic hot water at any one time. So the same concept I just described would be applicable to cooling as well, from the multiple heat pumps, and then operating some of the other heat pumps simultaneously to provide domestic hot water through these apartments. All right. As I stop there, I think this is a good point if anyone has any questions, especially around clarification of what I'm describing. Just unmute yourself and jump in. I'm going to shift over next to talking about some performance details for these heat pumps and modeling. So if you have any clarification questions about the schematic, this is a great opportunity.
Hey, John, I had a question. This is Matt Robinson from EPRI. Are you able to heat one zone and cool another zone?
This schematic design could be adapted to do that. I think we would typically refer to that as a 4-pipe style hydronic system. It could be done. I have tried to lean into a more 2-pipe style, heating only or cooling only approach, because it helps to reduce the piping infrastructure. And I do think that's important for reducing overall retrofit costs. And because I think that with this kind of modular array, there's like there's ways to group the arrays in a building that may have like simultaneous heating and cooling, like with cooling on the south and heating on the north side. You could just separate them to have separate 2-pipe systems.
Interesting. Thank you.
Yeah.
Looks like we have another question from Bill Lyons, which is,
Bill's,
can the heat from cooling be used to heat the domestic hot water load?
Oh, I dream of having air-to-water heat pumps that can do heat recovery from cooling as well. And I think that the general system concept opens up that future opportunity. but the manufacturers and monoblock systems we're working with right now don't have that function. But I hold it in mind every day, I'll tell you what. Yep. Okay, so we'll talk a little bit about performance and the modeling work. So as many of you know, the COP and capacity of air-to-water heat pumps depends especially on the speed or modulation of the heat pump and the leaving water temperature, and of course the outdoor temperature. But I really want to point out that adjusting the leaving water temperature for your heat pump has an enormous impact on COP. You know, at a design condition of say -5, you're talking about a COP of just below 2 if you're trying to heat with 55 degrees C water. And if you can reduce that down to 35 degrees C water, you have the opportunity to achieve a COP of 3.5 for this particular heat pump that we're representing in these charts. And so this is to highlight that there's a really important opportunity in the design of these systems to kind of, I say, maybe oversize or appropriately size your emitters to operate at a lower temperature. Of course, radiant heating and cooling systems are perhaps the largest heat transfer area that can facilitate the most moderate water temperatures. That might not be applicable to every design scenario, but there's a lot we can do even without radiant systems. Noting especially that many or well, most of our, almost all of our heating hours throughout a year are not at the extreme design condition. Just highlights that there's also a really important opportunity to incorporate and utilize outdoor temperature reset for the buffer storage that's providing heating and potentially cooling, depending on your climate and application and the extent to which you need dehumidification. But if you can design for, you know, your most moderate heating temperature days to operate, say, at 100 degrees Fahrenheit or below, and only ramp up to the highest heating water temperature during the coldest design conditions, you have a significant opportunity to reduce energy use. So in all of this work, Lawrence Berkeley Labs and Harvey Mudd College have been doing a lot of modeling work, advancing tools through software called Modelica, especially, and working to model these very detailed systems and their integrated controls. This is one of the buildings, kind of a co-op apartment building in Park Slope in Brooklyn, New York, that we modeled, comparing the COP, energy use of the air-to-water heat pump strategy here to a baseline multifunction style system. Focusing here on the left, these are a sample of some of our initial results for about a month of operation. Baseline heat pump systems shown here in red, and the COP of the air-to-water heat pump system here in green. And there are two main factors in the model that drive this quite large increase in COP. By the way, during the winter period for this application, LBNL estimated 25% reduction in electricity use for this air-to-water heat pump system compared to a baseline heat pump. But there's two main factors. One is the using an outdoor temperature reset to optimize COP of the system during low load periods. And the second, importantly, is avoiding low load cycling. And I'm sure that many of you know that a lot of the field studies out there with conventional split heat pumps, especially multi-split heat pumps, have been showing, let's say, surprisingly low seasonal COP values. And I would looking forward to learning more from others about what they know as the reasons for that, but a lot of the work we're doing is pointing to the impact of low load cycling, right? Basically that the heat pumps are spending a lot of time below their minimum turn down ratio. And if your part load ratio is less than 1 and your heat pump is cycling, your kind of COP degradation can become significant, as is shown from these curves, which was done from some research more than 20 years ago by LB&L. If anyone knows of some good field research looking at part load efficiency of conventional heat pumps, today's conventional heat pumps, I'd love to know about it. But let's look at this. This plot compares a space heating load and the capacity envelope for a conventional split air source heat pump, right? All of our hourly, annual hourly space heating loads are shown here in this cloud in green, and the orange lines show the minimum output and maximum output of this variable speed heat pump. And if, let's consider the scenario, you've designed the size of this heat pump to cover 100% of the design load, then for this heat pump, and this is a generally typical curve, almost all of the annual operating hours are below the minimum output of the heat pump. You really want as many green dots in this big alligator's mouth as possible, and this is just not getting there. And this is if you've designed, this is if everything works out so that the capacity of the heat pump can be in this position. If it's lower, like you choose a lower capacity heat pump, then you need to invoke some electric resistance, which is not necessarily bad. You can capture more of the part load periods. But I want to show you some of the things we've seen in our modeling. We've moved on most recently to using DOE's standard multifamily building that has 18 apartments in typically a 3-story arrangement, kind of with a south-facing row and a north-facing row. And one of the things that we've discovered from this effort is that there's large diversity between all of these apartments. And also, if we're adopting the strategy that practitioners have pointed us toward through our market research of utilizing 1 indoor unit per room, let's say 3 indoor units per apartment, then we end up in a design condition where, in order to accommodate the ability of having 3 indoor units and the minimum size that manufacturers offer for those indoor units, you're often forced into a situation where the outdoor unit has to be somewhat larger than the design heating capacity of each apartment. And also, we've learned that generally, the manual J calculations do not lead designers toward adopting different sizes of heat pumps for different apartments. So looking at the annual results from this building that I was just showing you, this is the annual heating load for every hour in the apartment with the maximum annual space heating load. And this is the heat pump that was selected by the contractor that we're working with, based on all the criteria that we've learned through our market research. So in this case, there's 0 hours that are within the dynamic operating period for that heat pump, and this is the apartment that has the lowest annual heating load, noting that there's significant diversity between north-facing and south-facing apartments and alike. So we want to address this low load cycling problem, and this is one of the key advantages offered by the kind of the modular multiplex array of heat pumps in a centralized fashion. What I'm showing in this plot now is the blue cloud is the hourly heating load for the entire building, all 18 apartments aggregated together and served by this central system. And the lines that I'm showing here now are the maximum output for the 4 air-to-water heat pumps that we've designed to include in that array, and the maximum output for only 3 running, 2 running, 1 of the heat pumps running, and here's the minimum output of only 1 of those heat pumps running. And this is just let's say 1 sample with 4 heat pumps. We could choose to have 5 smaller heat pumps or 6 even smaller heat pumps to satisfy the total kind of maybe 160,000 BTU per hour building heating load, right? And note that all of these heat pumps are variable speed, so we can hit kind of the dynamic output to match almost any of these heating hours until we get down below this minimum output, in which case the heat pump does have to cycle. But because these air-to-water heat pumps incorporate a small to moderate amount of thermal storage in the buffer tank, it means that the heat pumps can cycle in a way that doesn't degrade their COP. It's only the shorter cycling periods that degrade the COP of the heat pumps, at least as far as we understand. All right, so I know I only have 10 minutes left. I can talk a lot. I'll try to blow through the last couple topics here very quickly.
Yeah, and
First of
ideally
all,
we leave just a sliver of time for questions. 5 minutes.
I'll do my best. Just to note, in this work, we've been collaborating really closely with a startup manufacturer in the Pacific Northwest called Aris Hydronics. We worked with them to support their entry to the DOE's Easy Home Electrification Prize, where they were competing against 300 different competitors, trying to advance the best strategy to streamline electrification for homes. And we won. It was really exciting. I'm sorry to say that if you search the internet, the DOE website with the announcement has been scrubbed. But if you follow that link there on your screen, you can watch Aris's video about the design. There are some significant differences between exactly what I'm showing you and exactly what Aris has prototyped, but we're working closely with them. And by and large, the basic concepts are the same. So in that Easy Home Electrification Prize, we did a bunch of modeling, design iteration, prototyped this multi-family, multifunction type system. This prototype is set up in Aris's lab out in Portland. And I hope that you all have an opportunity to invite Robert Benjamin from Aris to a future meeting and have him present a little bit more detail about what they're doing. Also, as a part of that Easy Home Electrification Prize, we did a bunch of, let's say, initial costing using real data from retrofit electrification of medium to large multifamily complexes. And basically, we found that this strategy can provide large cost savings compared to the conventional approach. This is $3.2 million savings on a $12 million project, which includes all sorts of things like photovoltaics, roof replacement, other upgrades, design and engineering, and the like. So in this project with LBNL, we're currently working right now with TRC to do some even more detailed costing, where we've designed out down to the pipe sizes and valves and everything, this design strategy for an 18 apartment building, and they're working with contractors to price out this particular design as compared to the baseline retrofit strategy. And right now, we're all working together actively to do a retrofit electrification of a multifamily building in Vermont with this multiplex approach using Aris's R290 air-to-water heat pump systems. We'll actually only be electrifying the second floor of this building, but demonstrating the core system design. We've been working closely with Aris to design out like the modular components, like these indoor tanks, which include valves and circulators to allow the system to operate in the way that we've envisioned and modeled. Working with them to design out all of the electronics and the control systems. And right now I have a lot of my focus on advancing the whole system integrated controls, kind of with a lens for providing IoT connectivity to allow this whole system to work together in a streamlined way. We're planning to begin the install, well, maybe in 6 or 8 weeks. Everything is, all the equipment's in construction right now. And we'll leave it at that, and I'll open it to questions. I see Chris Granda, you jumped in on the chat here and you asked who's the pilot project manager at VEIC. It's Allison Ross that we're working with. Also Peter Schneider is directly involved. I forget if Peter works for VEIC or Efficiency Vermont. And I'll admit I don't know where the line between those organizations is. And Charles, I'm glad to see you note that this is the first multifamily presentation you've seen that makes economic sense. We hope so. Yeah, I'm really excited about. I think this provides I think it's going to provide a streamlined opportunity to do multifamily decarb.
Steve?
Yeah, so I'm curious, way back to the beginning, why are so many new circuits to the roof required in that typical setup? Is it because they didn't have condensing units on the roof because most of the units were cooled by window or wall units powered from inside the unit?
Yeah, fair question. Let's note that there's a wide range of multifamily archetypes.
Right.
Yeah,
of course. Yeah.
And we have zoomed in on this particular arrangement. This could also be a ground-mounted type of arrangement. You're definitely right to note that in a lot of like garden-style apartments, especially places like California or other places throughout the United States that have significant cooling needs, there are already split, centrally ducted air conditioners with furnaces. And yeah, to be fair, in that case, the strategy that we're targeting might be a little bit less advantageous. So we're really focused on especially colder climates, especially the Northeast and the Northern Midwest, that these older multifamily buildings that have limited electric capacity are such because they never really had cooling. And these are apartments that,
or they weren't originally built with cooling, but for the last 40 years they've had window units and wall units. Yeah. Okay.
You got it. Exactly.
Yeah.
And to note, there's a lot of places like this. We just were looking at a multifamily building in Los Angeles, where it's a garden style apartment, but each of those apartments has like old wall gas fired units, no cooling. And this is like really common scenario in the Northeast and the Pacific Northwest. A lot of the contractors we've been working with and talking to are out of the Pacific Northwest. And it's those two climates where I mean, I don't think I even had to mention in this call, like,
Yeah.
what's changing? Everybody needs cooling now. It's no joke.
Yeah. So that this strategy makes the most sense when there's already hydronic infrastructure for heating, but there is no electrical infrastructure for split cooling, right?
Well, I like to highlight that in this scenario, we think there's a big advantage, even in cases that don't have existing hydronic piping. Like if you're talking about in this building archetype doing all the retrofit for refrigerant piping and all the electric addition, air to water, we believe is a more streamlined approach. And I'll also note that there are some challenges with accomplishing this in buildings that have existing hydronic distribution, particularly insulating the piping to facilitate cooling.
Yeah.
But there are opportunities to kind of integrate those systems.
Got one final question before we close out. The cost comparison you showed is like a snapshot of a building. And I imagine, when I look at single family air to water heat pumps tend to be more expensive as a full, when you do like a full retrofit using an air to water heat pump ends up costing you more money than doing a few ductless mini splits and a heat pump water heater. Is there like a crossover point in terms of size? Is it not for duplexes or not for fourplexes, or what are you thinking there?
Yeah, good. A couple answers to that. One, I love your question, but I don't have the answer. I don't know. We haven't had the opportunity to kind of run a parametric cost modeling across a range of scenarios. But the other to note is that we believe that the kind of cost of air-to-water heat pump systems is currently artificially high because air-to-water represents less than 1% of the heat pump market in the United States. It would be really lovely if we could connect up with some folks out of Europe and look at what that pricing looks like in a mature market where more than 50% of the residential heat pumps being installed are hydronic, and they have the infrastructure and workforce capable of doing that. So I do want to be clear that a lot of the costing work that we're engaged in right now tries to make at least very reasonable assumptions about what near future mature costs could be for air to water systems.
Yeah, thank you. Thanks for that response. And thank you for presenting. I'll give the quick
welcome.
closing right now, and then we will adjourn. Let's see if I can jump us forward here. Okay. In terms of housekeeping, for our next speaker, I'd really love, there are two things that I think I really want to talk about. One is somebody who can give a good overview of the current standards and testing efforts that are underway, particularly at AHRI, as well as maybe calling out what's going on at Energy Star and other places where we might look to. We had a good presentation from programs folks about the qualified products list in the Northeast, but I'm curious to know more about these national efforts. And I also really want, I don't know if anybody has a canned presentation on this, but like I want to talk about distribution and distribution modifications and the tipping point to how much does it cost to put in a fan coil unit, and when do you need it to keep your leaving water temperature down, and kind of balancing all those considerations. If anybody knows anyone that would be great to speak to that, or has thoughts or a presentation in their back pocket, I'd love to see that. Our next meeting is August 22nd. Feel free to email me. Feel free to give me ideas for the next session. And thank you, everyone, for joining. Thank you, Jonathan, for coming. Bye, everyone.
Bye, everyone.
Thank you. Bye.